Welcome to this video on solving the problem snakes and ladders. In this session, we'll explore the problem statement, break it down step by step, and review potential approaches to arrive at an efficient solution. Let's dive in and tackle this interesting problem together. In this problem, we are tasked with solving the game of snakes and ladders. The game is played on an nxn square board, which is represented as a 2D integer array called board. The cells on the board are numbered sequentially from 1 to n-2, starting from the bottom left corner. The numbering proceeds in a bottom-up direction, alternating between left to right and right to left for each row. Now, each cell on the board contains one of two possible values, -1, which means there is no snake or ladder on that cell, or a positive integer x, which means there is a snake or ladder that moves you directly to cell x. You begin the game at cell 1, rolling a 6-sided die on each turn to determine how many cells you advance. If your movement lands you on a cell with a snake or ladder, you must follow it to its destination. Your goal is to find the minimum number of moves required to reach the last cell, n-2. If it's impossible to reach the last cell, you should return -1. To clarify the input and output formats, the board is given as a 2D integer array of size nxn. For any cell board, I, j, a value of -1 indicates that there is no ladder or snake in that cell. If the value is greater than 0, it represents the destination cell of a snake or ladder. The output of the problem is a single integer representing the minimum number of moves required to reach the last cell, n-2. If it is not possible to reach the last cell, the output should be -1. Let's take a look at some examples to better understand the problem. In the first example, the board is a 6x6 grid, where cells contain -1 unless there's a ladder or snake. For instance, cell 6 leads to cell 15, and cell 35 leads to cell 36. Let's see how the solution progresses step by step. In the first example, the output is 4, meaning it takes 4 moves to reach the final cell. Here's how it works: you start at cell 1 and roll a2 to move to cell 3. Rolling another 2 takes you to cell 5. Next, you roll a1 and move to cell 6. Since cell 6 has a ladder, you are transported to cell 15. Finally, you roll a4 to reach cell 35, and from there, you use the ladder to jump to the last cell, 36. The total number of moves is 4. Now consider the second example, where the board is a simple 2x2 grid. Let's see how this scenario plays out. In the second example, the output is 1, as it takes only 1 move to reach the final cell. Starting at cell 1, you roll a1 to move to cell 2, then roll another 1 to move to cell 4, which is the last cell. In this case, there are no snakes or ladders on the board, so the moves are straightforward. This shows how the problem handles smaller board sizes. Now, let's examine a third example where it is impossible to reach the final cell. In the third example, the output is -1 because the last cell, n-2, is unreachable. The board is a 3x3 grid, and all cells contain -1, meaning there are no ladders or snakes to help you progress. Regardless of the dice rolls, you cannot reach the final cell due to the lack of connectivity within the board. This demonstrates how the problem accounts for scenarios where reaching the goal is not feasible. Finally, let's discuss some constraints and edge cases to keep in mind while solving this problem. The constraints specify that the board is always square, meaning n == board.length == board, i.length. The size of the board, n, ranges between 2 and 20. The values in the board are either -1 or a number between 1 and n-2, and the first and last cells cannot contain snakes or ladders. Some important edge cases to consider include the smallest board size of 2x2, boards without any snakes or ladders, and scenarios where it's impossible to reach the last cell. Additionally, testing with the largest board size of 20x20 ensures that the solution is efficient. Finally, you should also handle cases where almost every cell contains a snake or ladder. These constraints and edge cases will help you design a robust solution for the problem. To begin with, let's consider the brute force approach. The intuition here is fairly straightforward. We simulate every possible move on the board starting from square 1. As you roll the die, which can take on values from 1 to 6, you move forward by that many squares. If you land on a square that marks the beginning of a snake or ladder, you immediately follow it to its destination. This process continues until you reach the final square, which is labeled as n squared on the board. While this approach is simple to understand and implement, it has significant drawbacks. The main issue lies in its inefficiency because it explores all possible paths. The number of states grows exponentially. This makes it impractical for larger boards. In essence, while it's a conceptually clear starting point, the brute force method sacrifices performance for simplicity, as it repeatedly revisits the same states and has exponential time complexity. Now, a more efficient approach involves using breadth-first search, or BFS. Here, we treat the board as an unweighted graph where each square acts as a node, and the edges represent valid moves, whether those moves are determined by a die roll or by snakes and ladders redirecting the path. Starting at square 1, BFS explores all possible squares in order of increasing distance, or the number of moves, from the start. This guarantees that when you first reach the final square, it's through the shortest possible path. To make this process even more efficient, we flatten the 2D board into a 1D array, which simplifies indexing. Additionally, we use a Boolean visited array to track squares that have already been explored, preventing redundant calculations. It's important to note that the board is numbered in a bottom-up pattern, alternating between left to right and right to left rows. Mapping these coordinates correctly is critical. BFS works particularly well here because it's designed for shortest path problems on unweighted graphs. In terms of complexity, BFS operates in n squared time since each square is visited only once, and it requires n squared space for the queue and visited array. This approach is efficient, guarantees correctness, and balances time and space considerations effectively. Finally, let's briefly touch on the depth-first search, or DFS, approach. While DFS could be used to explore paths from the start of the board to the end, it doesn't guarantee the shortest path unless every possibility is exhaustively explored. This makes it inherently less suitable for our problem, which prioritizes finding the minimum number of moves. While DFS can find all paths to the final square, its time complexity can become exponential in the worst case, making it computationally expensive and inefficient for our needs. After evaluating these approaches, we ultimately chose breadth-first search as the optimal strategy. BFS is well suited for shortest path problems, and its systematic exploration ensures that the first time you reach the final square, it's via the minimum number of moves. Flattening the board simplifies traversal, and the overall time complexity of n squared is efficient, even for larger boards. In contrast, the brute force and DFS approaches, while valid alternatives, are significantly less efficient and fail to guarantee optimal solutions. By balancing correctness and performance, BFS stands out as the most practical and effective choice for this problem. In this problem, our goal is to determine the minimum number of moves required to reach the final square, n squared, on an n by n board. The catch is that the game has snakes and ladders, which can either help or hinder your progress by instantly transporting you to another square. You start at square 1, and each turn, you roll a die to move forward 1 to 6 spaces. If you land on the start of a ladder or snake, you'll immediately jump to its destination. To solve this, we first represent the board as a one-dimensional array of size n squared. This simplifies movement calculations because every square corresponds directly to an index. If the square starts a ladder or snake, the value at that index will point to the destination square. Otherwise, it will point to itself. Next, we initialize our search. Since we are looking for the shortest path, we use breadth-first search, or BFS. The BFS queue is initialized with the starting square, square 1, along with a move count of 0. We also create a Boolean array called visited to track which squares have already been explored, preventing infinite loops and redundant checks. Now, we move on to the BFS traversal. As long as the queue isn't empty, we repeatedly process each element. First, we dequeue the current square and its associated move count. If the current square is the final square, n squared, we immediately return the move count since we've reached our goal. Next, we simulate rolling the die. For each possible outcome, from 1 to 6, we calculate the next square by adding the roll value to the current square. If the next square exceeds n squared, we skip it, as it's outside the board. Otherwise, we check the board array. If the square corresponds to the start of a snake or ladder, we update the next square to the destination square from the board array. This adjustment accounts for jumps caused by snakes and ladders. If the next square hasn't been visited yet, we mark it as visited, then enqueue the square along with the increment move count. This ensures that we continue exploring all possible paths while avoiding revisiting squares. If the queue is exhausted and we haven't reached the final square, which is highly unlikely with valid boards, we return -1 to indicate no solution. The use of breadth-first search here is key because it guarantees that we find the shortest path. BFS explores all moves at a given depth, or number of dice rolls, before moving deeper. This ensures the smallest number of moves is identified. The board's representation in a one-dimensional array allows us to handle snakes and ladders efficiently. With this setup, we can instantly jump to the destination square in constant time, avoiding unnecessary computations. Finally, the visited array is a critical component. It prevents revisiting the same square multiple times, which could lead to infinite loops or redundant calculations. By marking squares as visited, we ensure the algorithm remains optimal and avoids unnecessary processing. To implement this solution, we rely on 3 primary data structures. First, a queue is used during BFS to store pairs of the current square and the move count. The queue allows for efficient enqueue and dequeue operations, both of which run in constant time. Second, the board is represented as a one-dimensional array. This array provides a direct mapping from each square to its destination. Whether it's a regular square or one affected by a snake or ladder, the lookup is performed in constant time. Finally, the visited array keeps track of which squares have already been explored. With a size of n squared, this array ensures we don't revisit squares, keeping the algorithm efficient. In terms of complexity, the time complexity is O of north squared because each square is visited at most once during the BFS traversal. Space complexity is also O of n squared, which accounts for the board in visited arrays. When solving this problem, it's important to consider a few key edge cases. First, if multiple snakes or ladders start on the same square, the board representation must map to the correct final destination to avoid errors. Second, while unlikely in valid setups, the algorithm should gracefully handle boards where reaching the final square is impossible. This ensures robustness even in edge scenarios. Finally, for very small boards, such as a 1x1 board, the algorithm should still function correctly and return the appropriate result. For example, let's analyze a 3x3 board where the board array is given as 1, 4, 3, 6, 5, 10, 7, 8, 9. Starting at square 1 with a move count of 0, we roll the die and evaluate all possible moves. Landing on square 2 triggers a ladder to square 4, so we enqueue square 4 with a move count of 1. Similarly, landing on square 3 doesn't trigger any jumps, so we enqueue square 3 with a move count of 1. By continuing this process, we eventually reach square 9 in just 3 moves. Thus, the minimum moves required for this board is 3. Here, we begin by importing the D class from the Collections module, which will help us implement a breadth-first search. We define the solution class in the snakes and ladders method, which takes the game board as input. The board is a 2-dimensional list representing the snakes and ladders grid. We first calculate the size of the board, denoted by n, which is simply the length of the board. Next, we define a helper function called get_coordinates. This function maps a one-dimensional position on the board to its corresponding 2-dimensional row and column indices. Notice how the function adjusts for the zigzag pattern of the board. If the row number is even, the columns increase from left to right, but for odd rows, they decrease from right to left. This ensures that our coordinate mapping adheres to the rules of the game. After defining the helper function, we initialize a visited set to keep track of the squares we've already processed and a queue for the breadth-first search. The queue starts with the first square, labeled as 1, and an initial move count of 0. The while loop runs as long as there are elements in the queue, and within it, we dequeue the next square and its associated move count. We then simulate rolling a die, iterating over all possible outcomes from 1 to 6. For each roll, we calculate the next square we would land on. If the calculated square exceeds the total number of squares on the board, we skip it. Otherwise, we use the get_coordinates function to determine which position on the board this square corresponds to. If the board contains a snake or ladder at this position, indicated by a value other than -1, we will handle it next. If the board value at the calculated position is not -1, it means there's either a ladder to climb up or a snake to slide down. In this case, we update the next underscore square to reflect the new position dictated by the snake or ladder. Now, if this next underscore square happens to be the last square on the board, which is n*n, we immediately return the total number of moves taken so far plus 1, as we've successfully reached the end. Otherwise, if the next underscore square hasn't been visited yet, we mark it as visited to avoid processing it again and add it to the queue along with the updated move count. This ensures that we explore all possible paths in a breadth-first manner, guaranteeing the shortest path to the destination. If the queue is exhausted and we never reach the final square, we return -1, indicating that it's impossible to complete the game under the given conditions. This implementation ensures an efficient solution to the problem by leveraging the breadth-first search algorithm and handling the board's unique structure using the helper function and coordinate mapping. Here, we start by importing the necessary libraries and defining our solution class. The main method, snakes and ladders, takes a 2D integer array representing the game board as input. We begin by determining the board size, which is stored in the variable n. Next, there's a helper method called getCoordinates, which maps a 1D square index to its corresponding 2D coordinates on the board. This mapping is crucial because the board alternates between left to right and right to left row orientations. The logic accounts for this by checking if the row number is even or odd, adjusting the column index accordingly. After defining this helper, we initialize a set called visited to track the squares we've already processed, and a queue to facilitate a breadth-first search. The queue starts with the first square and 0 moves. Now, we enter the while loop, which continues as long as there are elements in the queue. For each square, we explore all possible dice rolls, ranging from 1 to 6. For each dice roll, we calculate the potential next square by adding the roll value to the current square. If this next square exceeds the total number of squares on the board, we simply skip it. Using our getCoordinates helper, we map the next square to its 2D position on the board. If the board has a snake or ladder at this position, indicated by a non-negative value, we update the next square to the value at that position. If the next square happens to be the final square, we immediately return the total number of moves taken, as we've reached the goal. Otherwise, if this square hasn't been visited yet, we mark it as visited and add it to the queue along with the increment move count. This process continues until the queue is empty. If no path to the final square is found, the function returns -1 to indicate the game is unwinnable. This breadth-first search ensures that we find the shortest path to the goal, as it systematically explores all possibilities level by level. To solve the problem, we start by analyzing a small 3x3 board with no snakes or ladders. The input board is represented as a 2D array with all values set to -1, indicating no special cells. First, we initialize the board size as n equals 3. The BFS queue begins with the tuple 1, 0, where 1 is the starting square and 0 represents the number of moves taken so far. We also maintain a visited set to track visited squares and avoid revisiting them. In the first level of BFS, we dequeue the starting square, 1, 0. For each dice roll from 1 to 6, we calculate the next square and its coordinates. For example, rolling a 1 leads to square 2 with coordinates 2, 1, so we add 2, 1 to the queue. Similarly, rolling a 2, 3, 4, 5, or 6 leads to squares 3, 4, 5, 6, and 7 respectively, which are added to the queue along with their corresponding coordinates. Since there are no snakes or ladders, all moves proceed normally to their calculated squares. Next, rolling a 6 leads us to square 7, which corresponds to the coordinates 0, 0. This completes the first BFS level. Moving on to the second BFS level, we dequeue the next square in the queue, 2, 1, and repeat the same process of simulating dice rolls. As we compute the reachable squares, we eventually reach square 9, which is the final square on the board. This happens in 2 moves, so the output for this example is 2. Now, let's consider another example, this time with a 4x4 board that includes a ladder. The input board has a ladder at square 7 that leads directly to square 15. We initialize the queue with the tuple 1, 0, and set up an empty visited set. The BFS process begins in a similar manner as before. In the first BFS level, we do Q, 1, 0, and compute the reachable squares for each dice roll. For rolls 1 through 5, the calculated squares are 2, 3, 4, 5, and 6, each added to the queue with their respective move counts. When rolling a 6, we land on square 7. This square contains a ladder that immediately takes us to square 15. As a result, we add 15, 1 to the queue, indicating that we've reached square 15 in just one move. In the second BFS level, we do Q, 15, 1, and simulate dice rolls. From square 15, we calculate reachable squares, eventually reaching square 16, which is the final square. This is achieved in 2 moves, so the output for this example is also 2. Now, let's examine a scenario where the board contains a snake that complicates the solution. In this example, we use another 3x3 board, but this time there is a snake at square 7 that sends the player back to square 1. As before, we initialize the queue with 1, 0, and start BFS. In the first BFS level, we do Q, 1, 0, and compute reachable squares for dice rolls. Rolling 1 leads to square 2, rolling 2 to square 3, and so on up to square 6. All these squares are added to the queue with their respective move counts. However, rolling a 6 takes us to square 7, where the snake is located. Instead of moving forward, the snake sends us back to square 1. Consequently, we add 1, 1 to the queue, indicating that we've returned to square 1 after one move. In subsequent BFS levels, the snake causes repeated setbacks, preventing us from progressing to the final square. Since there is no valid way to reach square 9, the output for this example is -1, indicating no solution is possible. The time complexity of our solution is n squared, where n represents the dimension of the board, which consists of nx n squares. This complexity arises from the fact that, in the worst case, we need to explore every square at least once. To determine the shortest path to the final square, we use breadth-first search, or BFS. During the BFS traversal, each square is visited exactly once, thanks to the visited set. For each square, we simulate up to 6 dice rolls, resulting in at most 6 neighbors to consider. These operations accumulate to a total of n squared BFS steps, proportional to the total number of squares on the board. Additionally, we use a helper function, get_coordinates, to map the linear index of a square to its 2D coordinates. Since this function performs only constant-time arithmetic operations, it does not increase the overall time complexity. Altogether, the BFS traversal and coordinate mapping combine to yield a time complexity of n squared. In the best case, where the target square is reachable in a single move, BFS terminates almost immediately, leading to an 1 time complexity. However, in both average and worst-case scenarios, the majority of the board needs to be explored, resulting in n squared time complexity. Now, let's consider the space complexity of the solution, which is also n squared. This is primarily determined by the data structures used during the BFS traversal. First, we have the visited set, which stores all the squares that have already been explored. In the worst case, this set can grow to include all n squared squares. Similarly, the BFS queue, which holds the squares waiting to be processed, can also grow to the size of the board in the worst case, contributing another n squared to the space complexity. The helper function, get_coordinates, does not use additional space since it relies purely on arithmetic calculations. Finally, the input board itself is passed as an argument and occupies n squared space. When we combine the space contributions from the visited set, the BFS queue, and the board storage, the total space complexity of the solution is n squared. By comparing our optimized BFS solution to a brute force approach, we can see a significant improvement in efficiency. A naive brute force method would involve simulating all possible dice rolls for every path across the board. Without using BFS or a visited set to prune redundant paths, this would result in an exponential time complexity of 6 n squared, due to the branching factor of 6 dice rolls and the depth of n squared squares. In contrast, our BFS solution reduces the time complexity to n squared, by ensuring each square is processed only once and leveraging the visited set to avoid redundant exploration. The space complexity is also n squared, which is far more manageable than the space requirements of a brute force approach. Mathematically, the BFS operations process each of the n squared squares once, with each step involving up to 6 constant time operations for dice rolls and coordinate mapping. This results in a total work proportional to n squared. Additionally, the visited set in BFSQ grow linearly with the number of squares, confirming the n squared space usage. Overall, the BFS approach achieves both time and space complexities of n squared, which are optimal given the constraints of navigating the board. When tackling the snakes and ladders problem, there are a few common mistakes to watch out for. First, ignoring edge cases can be a major pitfall. For example, if you roll a 6 when you're already on the last square, how do you handle that scenario? Similarly, encountering a snake or ladder can change your position unexpectedly, and failing to account for these transitions can lead to incorrect results. This is particularly important during interviews, where edge case testing is often emphasized. Another frequent issue is inefficient state representation. If you store redundant states or fail to optimize how you represent the board, your solution can become unnecessarily slow. Efficient state representation is critical for reducing both space and time complexity, which is often a make or break factor in solving large test cases successfully. Now, overcomplicating your BFS or DFS implementation is another trap to avoid. Introducing too many variables or repeatedly recalculating reachable squares can clutter your traversal logic. This not only increases the likelihood of bugs but also makes your code harder to understand, something interviewers are quick to notice. Additionally, not accounting for weighted shortcuts can lead to suboptimal solutions. For instance, while a ladder might seem beneficial in the short term, it could lead to a worse outcome later in the game. It's important to consider the long-term impact of every move. Finally, misunderstanding problem constraints is a surprisingly common mistake. For example, assuming the board size is fixed or overlooking the possibility of invalid inputs can trip you up. Misreading constraints can result in wasted time or missed edge cases, so always double-check your assumptions. To perform well in interviews, there are some key insights to keep in mind. Start by clarifying the constraints early. Always ask questions about the board size, dice values, and any special rules like how snakes and ladders are handled. When it comes to algorithms, BFS is your go-to for shortest path problems on a grid, as it guarantees the shortest path in an unweighted graph. DFS, on the other hand, is less suited for this type of problem unless explicitly required. Efficient state representation is also crucial. For instance, representing a 2D board as a 1D array can simplify your implementation. Pay attention to edge cases, such as the smallest possible board, situations with no snakes or ladders, or cases where the target is unreachable. Lastly, be prepared to discuss the time complexity of your solution. For BFS, this is typically n plus m, where n is the number of squares and m is the number of edges or dice rolls. There are also related problems that share similar concepts and can help deepen your understanding. LeetCode 909, Snakes and Ladders, is the classic board game simulation where BFS is used for pathfinding. LeetCode 127, Word Ladder, involves finding the shortest path in a word transformation graph, again using BFS. LeetCode 773, Sliding Puzzle, focuses on finding the shortest path for state transitions on a board, which is another BFS-based problem. Finally, LeetCode 490, The Maze, is a pathfinding problem that can be solved using either BFS or DFS. Studying these problems can help you recognize patterns and refine your problem-solving skills for similar challenges. Finally, let's discuss some alternative approaches and their trade-offs. One option is dynamic programming, where you calculate the minimum rolls required to reach each square. While this can work, it's often less intuitive and harder to implement compared to BFS. Another option is bidirectional BFS, which involves starting the search from both the beginning and end positions to reduce the search space. This can be faster in theory, but it adds significant complexity to the implementation. A third approach is greedy, where you always move to the square with the highest immediate benefit, such as the highest ladder. However, this method doesn't guarantee the shortest path, making it unsuitable for problems like this where optimality is key. Each of these methods has its strengths and weaknesses, so choose the one that best fits the problem requirements and constraints. To wrap up, we discussed the snakes and ladders problem, where we used BFS to simulate the shortest path on the board. Key takeaways include understanding graph traversal techniques and board-to-array mapping. Thank you for watching, and be sure to like, share, and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!